Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Christopher McKee, who's Emeritus Professor of Physics and Astronomy at the University of California, Berkeley. His research focuses on how stars form out of the diffuse interstellar medium of galaxies. Welcome, Chris.
Good to be here.
Yeah, thanks for doing this. So I want to start with one of your older papers to set the context for our discussion. And it's entitled A Theory of the Interstellar Medium, Three Components Regulated by Supernova Explosions in an Inhomogeneous Substrate. So supernova is essentially explosions, right, of stars. And so what are the three components you talk about here?
Okay, well, the three components were actually referred then to the gas in the interstellar medium of our galaxy in particular, which is what we focused on. So everyone, I think, is familiar with the Milky Way, and you can see the stars, at least on a clear night. But in addition, there's a huge amount of gas that's in the galaxy, about with a mass that is a little less than 10% of the mass of the stars. And this gas comes in a wide variety of different densities and temperatures. And in this paper with Jerry Oestreicher, what we did was to try to systematize all the available data and put together a coherent picture in which we divided the physical conditions of this gas into several different types. One was what we called the cold neutral medium, which is gas that was at a temperature of around 100 Kelvin, which is, Fahrenheit is like minus 370 Fahrenheit. So it's very, very cold by our standards, but actually not too cold by interstellar standards. Then there's a warm neutral medium, which is gas at lower density than the cold neutral medium. And because of that, it's cools less efficiently, and so it's hotter. And instead of being around 100 Kelvin, it's more like 10,000 degrees Kelvin. And then the new component that we introduced, or actually based on earlier work by Donald Cox, was a hot component of the interstellar medium, which was due to the supernovae. So when the stars, or sufficiently massive stars, thought to be above about 8 solar masses, end their lives after, say, a few to 50 million years, they can no longer support themselves, and they have a titanic explosion and release a huge amount of energy into the surrounding medium. They're also, when they're put on quite a light show as well, and there have been a few historical supernovae. I believe that one of them, for example, was said to have been as bright as the full moon. You can imagine looking up at the sky and seeing a star that bright. But now astronomers study these supernovae in other galaxies. and they
Yes.
temporarily become as bright as the whole galaxy. So anyway, they put out a huge amount of energy, and that produces shock waves, which race through the interstellar medium and heat up this cold neutral medium and a warm neutral medium and turn it into gas that has a temperature of order 1,000,000 degrees. And this gas then is at very low density, so it's hard to see. But even at that time, there had been initial X-ray and ultraviolet observations which indicated the existence of this medium.
So Chris, for my own understanding, so the Milky Way galaxy, our own galaxy, has, you said, about 10% of its weight, or 10, it's not weight really, 10% of its mass is in gas clouds,
Yeah.
right?
Mm-hmm.
And there are sort of, you described three different components: a very cold one at 100 degree Kelvin, moderately hot one at maybe 10,000 Kelvin, and then really hot. Is that right?
Yes.
And so it's sort of, am I understanding it correctly that when a supernova explosion happens, you essentially have sort of a shock going through this fluid that is at various densities and temperatures, right?
Correct.
And so what are the implications of that in that context?
Well, as I mentioned, the main thing that happens when this shock wave goes through the medium is that it heats it up. The shock waves that we're familiar with on Earth are sonic booms, but these are actually extremely weak shock waves. The shock waves that occur as a result of a supernova explosion are many, many orders of magnitude stronger. So they can take gas and at the start, you can start off maybe at 100 Kelvin and get heated up to actually even billions of degrees when the supernova, the remnant of the supernova is young. And then as it expands, the typical temperature that it heats the gas up to is more like 1,000,000 degrees.
And so is a shock wave really taking this gas clouds away from the supernova, or what happens afterward?
Yeah, and so the first comment I'm about to make, only I sort of worked on later, was that before the star explodes as a supernova, it already pushes gas away. These massive stars have very powerful stellar winds, and they also have produce a lot of ionizing radiation. And both effects tend to push the gas away, so that when the supernova explodes, it's probably going to explode in a low density medium, but then the shock wave runs into these clouds that have been pushed away. And just as you suggest, they pushes on the clouds and accelerates them away from the supernova. And in fact, many years before our work, Lyman Spitzer, who was really the father of the theory of the interstellar medium, had suggested that supernova explosions could account for the random velocity that you see in interstellar clouds. And we confirmed that in our analysis.
Okay, so how often does a supernova happen within our own galaxy?
Well, that's a very interesting question. They're predicted to happen about once every 50 years. But the last one that we know about was, I think it was Kepler's supernova. There were two actually around, 400 years ago. There were two that occurred in quick succession, and I'm sure contemporary astronomers just wish that they could have been living in those days, but with modern instruments to study them. Then a younger remnant, which is well studied, is called Cassiopeia A. That occurred only about 250 years ago, as I recall. That it's not clear that it was ever observed. It is behind a lot of interstellar dust that obscures the supernova, but it's been very well studied since then. But so, and then I believe there's one other young remnant that has been detected since. But that the number of young supernovae remnants that we see is much less than the one for 50 years that's predicted. So hopefully we will be able to see some of these young remnants, as we get more powerful instrumentation. Because they would mainly occur in the disk of the galaxy, and as I just mentioned, I've been talking about the interstellar gas. In fact, all this gas contains little dust particles, and the dust absorbs the light and means that you really can't see that much of the light. So when you look at the Milky Way, that's, as you know, it's a very faint band of stars, but that's because we're only seeing the stars that go out to maybe a few thousand light years away. But the Milky Way is much, much bigger than that. And if there were no dust, then the stars, we'd be able to see a lot more stars, and the Milky Way would be a lot brighter. So the supernovae that have occurred recently quite possibly have been obscured by all this dust, and so we just haven't been able to see them yet.
And so based on the number of stars in the galaxy, our expectation of the frequency of what we of a supernova happening in the galaxy is about 50 years, 1 per 50 years.
Yeah.
But we don't see that. Are there any? Is it just sort of a random occurrence? Sort of a quiet period, or is there something more to it?
Well, it's quite possible that we're just in a random period where there are not as many as usual. As I mentioned, at around 1600, they were very common. There were 2 within 30 years, I believe, and the 2 that were close enough so that they could actually be observed with the naked eye. It's a combination of the fact that we appear to be in a low period, and then, as I said, most of them should be occurring in the disk of the galaxy, where they're very hard to observe because of all this obscuration.
So, if a powerful supernova happens, what does it could create some issues for us, right? So what is sort of the safe distance for a supernova from an Earth's perspective?
That is a very good question. I don't really, and people have looked at that. I'm not, aware of their results, so I can't give you a detailed answer. But there are several different effects that occur. You would get the enormous flash of light, and it's possible that would have a destructive effect on the ozone layer. So, which would then allow ultraviolet radiation from the sun to reach the ground, and that would be very bad for all life on the ground. So, in fact, there has been an explosion, not a supernova explosion, but an explosion on a magnetized rotating neutron star with a very strong magnetic field called a magnetar. And that explosion actually did ionize the upper part of the Earth's atmosphere. So if you can imagine, this was, I believe, around 30,000 light years away. So it's not at all near the sun. And despite that, this enormous burst of energy was able to affect the atmosphere. So that's one thing that will happen. Another thing that occurs is that these supernovae accelerate cosmic rays. So cosmic rays are particles that are moving at nearly the speed of light, and they pervade the galaxy. And we're protected from them to some extent, first of all, by the solar wind, which tends to keep them out. Then the ones that are able to get in through the solar wind and get to the location of the Earth, we have a magnetosphere, which then also prevents them from striking the Earth. But the supernova, if it were near enough, would produce a much higher intensity of cosmic rays that would have many more relativistic particles coming in. The ones that do penetrate, the ones that have high enough energy to get through both the solar wind and the Earth's magnetosphere, come all the way to the ground. And in fact, even right here in our country, there's there are cosmic rays going through us all the time. And if you go to a place like Denver, which is, a mile above sea level, there's less atmosphere shielding you from the cosmic rays. So actually you get a more intense radiation from these cosmic rays in Denver, say, than you do here in Berkeley. But if you were near a supernova, say within from 100 or 200 light years, then it's likely that you would be exposed to a period maybe of thousands of years where the intensity of these relativistic particles would be much, much higher, and that could have getting a lot of radiation is certainly not very helpful.
So the neutron star explosion you mentioned, 30,000 light years away, we have some observable impact on the Earth's atmosphere. So is it fair to say anything within, let's say, 100,000 light years could potentially have an impact?
Yeah, I think of supernova, if it, I have to be, actually, I don't remember what the instantaneous flux was. A supernova yields far more energy than this explosion on this magnetar. But what happened with the magnetar was it was an extremely brief flash, so that the energy that it did release was released in a very short period of time. And so I actually don't know how the intensity of that radiation would compare with the intensity of the radiation from a supernova, which would go on for typically, say, a quarter 100 days or so, instead of just a brief flash.
And this waves are really traveling at the speed of light. So is it so if something happened, let's say today, at 100,000 light years away, we wouldn't know that happened for 100,000 years.
That's correct.
And so is there anything that, I guess the information cannot travel faster than light. And so we wouldn't know if anything has happened, and something is traveling toward us, if it's not within that window of information.
That's correct. So it's true that when I talk about, so I said that there were two supernovae that occurred a few hundred years ago, and that Tycho and Kepler were able to observe them. But in fact, they're thousands of light years away. So that in fact, if you wanted to look at current time, they actually occurred thousands of years ago. But the light just reached us. So we say, well, we just keep track of what's going on as we measure it. And of course, this goes on when you look at distant galaxies. If they're millions of light years away, that means the light we see actually originated millions of years ago. And it goes all the way back to the Big Bang. If you look at the cosmic microwave background radiation, that radiation was emitted a few 100,000 years after the Big Bang. So that's over 14 billion years ago, but we're just seeing it today.
Are there some empirical, some sort of a heuristic that basically says what the energy output would be when a supernova happens, based on the characteristics of the star?
Yes. Now, actually, the total energy that's emitted in a supernova, the typical one at least, seems to be sort of independent of the mass of the pre-supernova star, and that's because there's sort of a convergent stellar evolution. The star is just like the sun, is hottest in the middle, and that's where the nuclear reactions are going on. Well, as a massive star evolves, the nuclear reactions also occur most rapidly at its center. And so first it burns hydrogen to helium, then helium into carbon, and then it starts building heavier and heavier elements until actually you build up a core of iron. And you can't really release any energy by fusion for elements that are heavier than iron, then that's fission. As you know, if you have atomic power, that you have uranium, so that's much heavier than iron, and you release energy by having the nucleus break apart. But whereas with light elements, then you can release energy by bringing the elements together. And so iron is right in this sweet spot, which is in between. So once you get to that, and the maximum mass that that core can have and still be able to withstand gravity is a little bit more than one time the mass of the, than one solar mass. And so that's sort of, no matter how big the star was to start with, it winds up with this center, which has at about the same mass. And then when it's burned up and it can no longer release enough any energy by nuclear reactions, the heat leaks out, and then it's no longer supported. So it starts to undergo a collapse, and that releases a lot of energy that actually then causes an outward going shock. So you have simultaneously something that's collapsing down to much higher density, to the density of a neutron star, and an outward going shock that then blows the outer layers of the star away and creates this extremely luminous outburst.
So regardless of the initial conditions that you start with, the size of the star, ultimately you end up with approximately one solar mass core, right, of heavy elements. And so when supernova happens, that core is sort of standard. Did I understand that correctly?
Now I'm describing the type of supernova that occurs for massive stars more than about 8 times the mass of the sun. And those are called astronomically, they're type 2 supernovae. But there's a whole different type called type 1 supernovae, which actually occur in low mass stars. And so they're, how they occur is actually a topic of very active research now. And it's thought that in many cases, they occur as a result of being in a binary system. And then depending on what happens in the binary, you can make the one of the stars in the binary get more massive than can be supported by pressure, and then it collapses and makes a supernova. And this, it turns out that the characteristic mass of those stars is not that different than this mass I was talking about before. It's a little bit more than one solar mass. May be familiar with the famous astrophysicist Chandrasekhar, and he very famously, I believe it back in the 1920s, actually predicted that there was a maximum mass that stars like the sun could have, and when they were very, very old and exhausted all their nuclear fuel. And that is, so that's called the Chandrasekhar mass. And it is about 1.5 times the mass of the sun. And if you're in a binary and you can transfer mass from one star to the other, and yet so that star gets more than this mass, then it will undergo a collapse and explode.
So the standard candles that we talk about, that's type 2 or type 1?
Those are type 1.
Those are type 1. So it doesn't matter wherever this happens. We could standardize based on the intensity of light, how far it is.
That's exactly right. So I mentioned that there is a tendency for the type 2 supernovae that occur in the massive stars to be similar, but in fact, there are a lot of different kinds of type 2 supernovae, and astronomers have classified them. And that's, again, a very active area of research. So they're not nearly as good as standard candles. Their luminosity can vary by a factor of 10 or so from one supernova to another. Now, the type 1 actually occur, there are different kinds of type 1s, and the standard candles are the so-called type 1A, which are the classic ones I was talking about with this Chandrasekhar mass. And then it is, because that Chandrasekhar mass is well determined, you would think that then all the supernovae should be the same. But Mother Nature is much more complicated. And so we found that actually even the type 1a supernovae can have different brightnesses. But it was discovered that it's possible to sort of standardize them, that depending upon the time evolution of the brightness, you could then take that information into account and determine what the intrinsic luminosity was. And so that trick was good enough so that it was possible to know what the actual luminosity of the star was. And then just as if you're thinking about, you're outside and you have a friend with a flashlight, as the friend walks away, the flashlight will get dimmer and dimmer. And so you could actually figure out how far away your friend is by, how bright the flashlight was. And that's because you would know how bright it was intrinsically. Well, the same thing is true with a supernova. If you know how much energy it's emitting per unit of time, then the farther away it is, the dimmer it will be. And by measuring how bright it appears, you can figure out how far away it is. And it was through observations of that type that one of my colleagues here at Berkeley, Saul Perlmutter, and his collaborators was able to determine that the universe expansion is actually accelerating, whereas prior to that point, most people had been assuming that the universe was decelerating and would eventually recollapse.
Yeah, so that's one of the techniques used to compute the cosmological constant, right? How fast the universe is expanding, and I guess there are some controversies around, not necessarily controversy, but the numbers are not really matching from different observations.
That's right. No, it's a very interesting problem. So I'm old enough to remember the classic argument between two very famous astronomers, Alan Sandage at Caltech and Gerard de Vaucouleurs at the University of Texas. And they were trying to measure the Hubble constant, which was made famous by Edwin Hubble. And that is how fast the galaxies are expanding away. Now, if you think about our space, it's kind of expanding. So one analogy which astronomers like to use is imagine that you are making raisin bread and you put a bunch of raisins in some dough, and then you put in some yeast to make the dough rise. Well, you could start off with a small ball of dough, and then as the yeast got to work, the dough would expand, it would get larger. And then what you would think about, if you look at all the raisins, they would see, if you were stood on one raisin, you would look out and all the raisins that you looked at would be moving away from you, and the raisins that were farther away would move away faster. And so that's basically the Hubble expansion. And they were able to go ahead and measure this, but the controversy was Sandage said that it was 50 kilometers per second per megaparsec. That means if you're 3 million light years away, that's the megaparsec, then something would be moving away at 50 kilometers per second. Whereas the Vaucouleurs said, no, that's totally wrong. That's 100. They were off by a factor of 2.
Yeah.
And then, interesting enough, with more precise measurements, it turned out that the correct answer was halfway in between. It's about 70. So, but now there's a controversy because, as you just alluded to, that if you make observations, cosmological observations of the microwave background, you tend to get numbers that are a little bit lower than if you use these standard candles. But instead of a difference of a factor of 2, now it is less than 10%. So we're getting to be much more accurate. And people are working very hard on this, and I think that regardless of how it turns out, we're going to learn a lot. So the conventional explanation would be that somehow one of the assumptions that has gone into estimating these distances are wrong. But since people have worked on that very hard, that would that'd be very surprising. We would learn a lot just from discovering that error. The other and more exciting possibility is that actually this simple picture we have in which we have a simple Einsteinian universe with a cosmological constant is not exactly correct, and that maybe the cosmological constant is a function of position or of time. And so there's some new aspect of physics that's coming in and causing this change. So when you measure the Hubble constant from the microwave background, which is based on things that happened 14 billion years ago, and compare that with observations of supernovae, which maybe occurred only 5 billion years ago, the fact that they're different answers means that there's some new physics. So I think we'll understand that within the next decade.
Yeah, that'll be very exciting. So on the supernovae measurement side, Chris, since we have a lot of them, couldn't we sort of derive, if the cosmological constant is time and location dependent, couldn't we actually see that by looking at different supernovae?
Well, that's one of the things that people are doing, is they're trying to get much more precise data to try to pin down whether there is any effect like that. And the simple model actually does just have the cosmological constant that Einstein put in, which he called it his greatest blunder. But then now it's been resuscitated, and it explains all the data we have now. But one of the major telescopes that's going to be coming online in 2 or 3 years is called the the Rubin Observatory. It's the Large Synoptic Survey Telescope, and that is going to look at the whole sky, at least the whole sky visible from Chile, and every 4 days. And so it's going to be an ideal instrument for measuring time-dependent phenomena like supernovae. And we will learn a lot more about that. It's also going to look at a different effect, which is gravitational lensing. You'll be able to get very detailed pictures of galaxies and see how their shapes are affected as the light propagates to us. And you can analyze that and see whether there are any new effects that are coming in due to that.
Yeah. We'll take a quick break, Chris. When we come back, we'll talk about the other papers in the area of theory of star formation.
Okay, great. I'll talk to you in a few minutes.
Yeah. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. Chris, we were talking about supernovae explosions and potentially the impact of supernovae explosions on us, how frequent they occur, and really different types of supernovae and the measurements of some of those that could give us some clues as to even the expansion of the universe. I want to go into another paper in 2007 on the theory of star formation. You say a conception of star formation has emerged in which turbulence plays a dual role, both creating overdensities to initiate gravitational contraction or collapse, but also countering the effects of gravity in these overdense regions. And so two opposing effects. And so both of these have an impact on how ultimately the star is formed.
Yeah.
How does it work? Yeah.
Yeah, that's correct. So one of the observations of the interstellar medium had shown that it was turbulent. But this aspect of the interstellar medium wasn't really focused on very much until the very end of the 1990s. And then people increasingly started looking at that. And one of the major reasons they were able to, or at least became more uppermost in theorists' mind, was it was possible to do numerical simulations. And you could actually then see what happened in the computer when you have gas that showed the velocity that you actually observe. And it was recognized that under those conditions, you essentially recreate, you have a turbulent situation. So turbulence in the atmosphere and the ocean is responsible for lots of phenomena. And it's one of the classic problems in classical physics that has never really been solved. So we know a lot about turbulence, but there's no sort of first principles theory that can actually predict all the phenomena that you see. So that is actually then something that physicists are studying today. Now, in the interstellar medium, as we discussed earlier, we have these different components of gas. And there's another very important component that Oostreicher and I did not consider in our original paper, and that is the molecular gas. And gas is even colder than the cold neutral medium. It has a temperature more of about 10 or 20 degrees Kelvin. And that means that sound travels very slowly in those clouds. So the speed of sound actually depends on the temperature of the gas, because that determines how fast the molecules are moving. So because you have a very slow speed of sound, but you observe that these velocities in the clouds are much faster than the speed of sound, that means that instead of having the type of turbulence we have on Earth, which is where the velocities are very small compared to the sound speed, you have turbulence where the velocities are very large compared to the sound speed. And so this is something that people have now devoted a lot of work in studying numerically, and we have a better understanding of it. And as we mentioned in that review article, you have these two competing effects. So one of the things is, since it's supersonic, what that means is that I have a velocity of the flow, which is very large compared to the sound speed. And that means that the pressure that occurs when two pieces of this gas collide is very high, and it compresses the gas. So when go ahead.
It is the same. I know that when supersonic aircrafts travel, you get this booms, right? Is that the same sort of thing?
Right. So the sonic boom, of course, when you actually hear it, it's the plane is far away, and so that sonic boom is a very, very weak shock. We're talking about very strong shocks, and when you have the space shuttle, when it re-enters the atmosphere, can create a shock that would might have a velocity compared to the sound speed that's similar to the shocks we're talking about.
Okay.
And if you've seen the pictures, I guess, of them where you can see that this may be an artist's visualization. You can see it's very hot gas which is surrounding the nose of the space shuttle as it comes in, and so that's what happens. You get the gas gets compressed and it gets heated. Now, in the case of this molecular gas in the interstellar medium, it can cool very efficiently, so it doesn't get heated that much by the shocks. It mainly just gets compressed. And one of the things that astronomers discovered, and most of this work was done after the paper we talked about before that I wrote with Jerry Oostreicher in 1977, they discovered that stars are forming in this molecular gas. In fact, all the stars that we observe that are forming in this very cold, dense molecular gas in the interstellar medium. And so because it's supersonically turbulent, that means that you can compress it, which is good. You need to get the gas to be very dense in order to make a star. On the other hand, if I look at it from a larger scale, if I try to compress a turbulent medium, I will have all these shock waves running around inside it. And when I'm pushing on it, if a shock wave hits me where I'm pushing, it will try to push me away. So it also, this turbulence can act to resist gravity as well as causing compressions.
Yeah.
And,
so I remember, Chris, long time ago, I did some work in engineering, and we used to use this computational fluid dynamics software, to sort of model airflow and things like that. So the numerical simulations that you talk about here are similar to that CFD type models.
They are similar, except the ones I'm talking about, most of the CFD models assume that the flow is very slow compared to the speed of sound, unless you're dealing with, a supersonic aircraft. But typically you assume, I'd imagine, particularly as you're doing, and so that has the advantage that you can assume that the fluid is incompressible. And so that simplifies matters. Now, a complication that you have in engineering that we generally don't have is that you have boundaries. So if you're trying to simulate an aircraft, then you have this very complicated shape of the wing, and you have to deal with that. Whereas we're out in the middle of space, and so there are no boundaries. Then that simplifies the thing.
Yeah, so you don't have a lot of interactions, but the behavior inside is quite different because of the just the speed at which it's collapsing. Right.
Yeah, I didn't catch your question. Could you repeat it?
So you don't have interactions with other surfaces and so on, but inside the star itself, everything is moving at a speed that is much, much higher than the speed of sound.
Right. No, not inside the star, but inside this molecular cloud. So so the molecular cloud is can be a few light years to hundreds of light years in size, and that's where you have all this turbulence. And what you find is typically that as you look at larger regions, you find that the average turbulent velocity gets larger and larger. And that's something that you actually see in earthbound turbulence as well.
So these effects that you talk about here, they are sort of necessary conditions for star formation, or it's something that you're observing in certain scales?
The necessary condition for the stars to form is that you be able to accumulate enough gas so that the gravitational force exceeds all the forces that are trying to support it. So the star can be supported by gas pressure. If you look at the sun, for example, it's in a nice equilibrium in which you have the gas pressure is pushing out and the gravity is pulling in, and the sun is just sits there and is very quiescent. In the molecular gas, when I'm talking about a molecular cloud that's many light years in size, and it has all this turbulence in it, then there are regions which will get compressed and get to high enough density so that the gravity can overcome the thermal and turbulent pressure inside that gas, and then that cloud will start to collapse and will form a star.
So the turbulence acts like a sort of a pressure pushing it away against the gravitational contraction.
Yeah. So the turbulence tends to resist. If I think of a given volume of gas, the turbulence tends to resist compression because it's basically, in the absence of gravity, if you have a turbulent region, it will tend to expand. And then so that's resisting the attractive force of gravity. You have to get enough gas in and have the turbulence be weak enough so that the gravity can overcome this turbulent pressure. And you also have thermal pressure. If for particularly in regions where stars of solar mass or less form, then you eventually get to a high enough density so that the thermal pressure is actually bigger than the turbulent pressure. And then again, it's a question of trying to look at the balance. There are small cloudlets that are seen where you appear to have a very good balance between thermal pressure and gravity, but instead of being the size of a star like the sun, they are a light year in size. But these will then tend to accrete more material, and at some point they will, as you add on more material, the gravity gets stronger and stronger, and eventually it will collapse and form a star.
Yeah, so it's set of a complex set of processes that ultimately settles down into a star.
Mm-hmm.
And I guess, so how long does it take for a molecular cloud to form a star? Is that measurable?
Yeah, so astronomers have spent a lot of time measuring this. They can look at stars at different stages of evolution and also of these clouds at different stages of evolution, and try to then, if you can essentially determine the lifetime of one of the phases, you can then, by looking at how the other phases, how many of them there are, you can get relative ages. And so typically people think that for a star of the mass of the sun, it's going to form in a few 100,000 years from this, once you have sort of accumulated the amount of molecular gas that you have. Now there's a question as you go to more massive stars, if they were to form exactly in the same way that low mass stars did, then because they had more mass, they would take longer, and they might say, well, maybe they'd take 1 million years to form, or even millions of years to form. But on the other hand, it appears that these stars, on the contrary, tend to form from a denser gas that is internally turbulent, and as a result, they form perhaps even in a shorter period of time than the less massive stars, so less than 100,000 years.
And so, since these are dynamical processes, so the gravitation, the turbulent space pressure, the thermal pressure, so are there objects, Chris, out there that sort of never really settles into a star but goes back and forth in some way? I'm just I don't know anything about it, just asking the question.
Sure. No, that's undoubtedly the case, that when we're talking about this turbulent motions, then I mentioned that you have these shock waves coming. They're essentially creating dense regions, and then there's this question as to which is larger, the internal pressure due to turbulence and thermal pressure, or the gravity. And in some cases, the internal pressure will be greater, so that this density concentration will just be a transient and will expand back out. And there could also be cases, and this is a very interesting situation, if you look at how stars might form at the centers of galaxies, where you have these supermassive black holes, then there's also very strong shear effects, because as the gas is sort of orbiting around the black hole, then as you go out farther, the gas moves more slowly. So you can take a gas cloud and stick it near a supermassive black hole and watch it go around. And if the gravity is not strong enough, it will go ahead and just get sheared apart into a ring, and that would prevent it from.
So the balance you need, so to speak, to ultimately form a star is a function of how far the star is from the center.
Yeah. So, well, if you are in the vicinity of the center, then that is a very strong effect. But when you're out where we are, then it doesn't really matter that much.
But
I would like to make one other comment on that, though. That
yeah,
we were talking about the formation of a star. If I say, well, how does the molecular cloud form? Remember, the
yeah.
stars are going to be small pieces of this big molecular cloud. Well, how did the cloud form? And out here, even where we are, which is between 20 and 30,000 light years away from the center of the galaxy, then the forming of this molecular cloud, you have to overcome this shear effect that I was talking about. So the gas, as you get farther and farther away from the center of the galaxy, it actually is moving at about the same velocity, but because it has farther to go around, it means that 2 points at a different distance from the galaxy will gradually separate from each other. And you have to have the gravity in the molecular gas be large enough to prevent that from happening.
So the intensity of star formation, isn't it close? Isn't it more as we get closer to the center?
Yes, and that is most likely due to the fact that you have more molecular gas there. Now, actually, in our galaxy, it's been recently realized that it is what's called a barred spiral galaxy. So instead of just being a nice smooth disk with spiral arms, when you get in within about 10,000 light years of the center, there is a bar. I don't know if you've seen pictures of some barred spirals. They're quite dramatic. And then when you get sort of within that distance, or maybe a little bit closer, the rate of star formation actually goes down a lot. Then when you get right near the center, within hundreds of light years of the center of the galaxy, then the star formation rate goes up again. But there does seem to be sort of a hole in the star formation in the galaxy that's presumably caused by this bar.
And this molecular cloud, Chris, that is basically hydrogen gas or something different?
Yeah, it's mainly composed of molecular hydrogen. And one of the things that is very interesting is that molecular hydrogen is itself very difficult to observe. And unless you can get it very hot. So in the cold interstellar medium, it's essentially invisible. And as a result, what astronomers have done is to look for other molecules. And the most abundant other molecule is carbon monoxide. So, if that's on Earth, we know that's poisonous to people, but out in space, it doesn't really matter. So that is the second most abundant molecule after molecular hydrogen. And astronomers have studied this in great detail. So it's from studies of the CO molecules that we have the most information about the large-scale structure of molecular clouds.
Yeah. I want to touch on one other phenomenon, another paper, radiative feedback processes and implications for the initial mass function. So this is, again, a phenomenon during the formation of the star.
Mm-hmm.
So what is the radiative feedback process?
Okay, so when a star forms, it emits radiation, and that heats up the surrounding gas. So as we were discussing earlier, when you're forming a star, you have this competition between gravity trying to pull the gas in and make the star, and the pressure which is pushing out and trying to prevent that from happening. So the pressure increases with the temperature. It's just linearly proportional to temperature. So as I make the gas hotter, then that increases the pressure and helps it resist gravity. So when I go ahead and I start forming stars in a molecular cloud, they would then start emitting radiation, and they heat up the gas in its surroundings. And that then means that the gas in its surroundings can no longer undergo gravitational collapse. And So the characteristic features of this initial mass function, which is sort of what is the initial distribution of masses of stars that form, is strongly determined by that. As soon as you start forming these stars, it prevents larger stars from forming.
Yeah, so sort of like once the star is fired up, so to speak, then it's going to push away what is remaining in the neighborhood.
Exactly.
It can't use it anymore.
Right. Now, this radiative feedback gets far more dramatic when you get to more massive stars. So in the for low mass stars, actually, it doesn't really push the gas away; it just kind of heats it up and prevents it from undergoing gravitational collapse. But when you get to massive stars, then the massive stars produce so much radiation that the pressure of that radiation can push the gas away. And these massive stars also have very powerful stellar winds, and that is, they blow gas away from the star itself, and that can push gas away as well.
Right. So in conclusion, Chris, you have done a lot of work in this area. So as you look forward, you continue to do research in this area. So what is the area that's most exciting for you? And where do you think we will find interesting things in the next 5 years?
I think that in the next 5 years, at least on the theoretical side, one of the most interesting things will be trying to get more insight on the formation of the very first stars. And so these are stars that formed, maybe only 100 millions or hundreds of millions of years after the Big Bang.
Yeah.
And all those stars that had a mass more than about 80% of the mass of the sun would have already essentially burned out all their nuclear fuel, and they would be dark. So they will not be able to see them from their light. And we will learn more about them, though, because through gravitational lensing, as one of these stars passes in front of a luminous star, then it bends the light, and the new telescopes, such as the Rubin Observatory telescope, are going to be able to see that. And there's also a mission that we launched in space, the Roman Space Telescope, which will carry out large surveys, and that will help in this regard as well. So if I wanted to, let me just make one other comment.
Yeah.
That's one way you can try to see these very old stars. The other way is what's called galactic archaeology, and that is to look at stars which are more massive than that, so they actually have still emitting light, and look at their composition. The very first stars would have had no heavy elements in them, so they would just be hydrogen and helium with a very tiny amount of lithium, perhaps. But that's all. And you can now look at the spectrum of the stars and see whether there are any heavy elements. So far, we haven't seen any of those. We've seen some that have much less heavy elements than the sun. And those studies are going to be really amplified in the next 5 years. And finally, the James Webb Space Telescope is going to be able to see very distant, won't be able to see individual stars, but it will be able to see clusters of these stars when they first formed. And that will also provide very valuable information. On the theoretical side, the computational capabilities are really just amplifying very rapidly. And I think within the next 5 years, we'll be able to carry out far more accurate simulations of the formation of those stars.
Yeah. In exciting times, there is still a lot to be found, a lot to be done on the theoretical side. A lot of telescopes going out, both in space and moon, and on Earth as well. So a lot of data is going to come in, and as you say, the computational capabilities are increasing. So it's exciting time for astrophysics.
You're exactly right. It's going to be very exciting. And I think that particularly some of the planned telescopes will provide dramatic images also that I think everybody will be able to appreciate.
Yeah. Excellent. Chris, thanks so much for spending time with me.
Sure. Well, thanks for the invitation.
Absolutely. Good luck with the research.
Okay.
Thank you. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.